In part 3 of section 14, we need to discuss a little more closely what the purpose of stating the multiplicity of a zero is. Now, what we're going to be most interested in is the multiplicity of the real zeros. Let me emphasize the word real there. And the reason for that is because every time we graph a function, we are graphing it using real number lines. So anything that's imaginary or complex is not going to have any business in the graphing that we do. So the multiplicity is going to tell us specifically how to be able to graph our x-intercepts. Because what we need to realize is that your real zeros are going to represent the x-intercepts of the graph. So how do x-intercepts come about? They come about in one of two ways. X-intercepts are places where you either touch or where you cross the x-axis. So the multiplicity is there to help tell us which one of those behaviors we should expect to see. Are we going to cross the x-axis, or are we just going to touch the x-axis? So I have a summary here with this table of all the different multiplicities that we're going to encounter. There are certainly higher degreed multiplicities, but we're going to stick with just 1 through 4. And example 14.7 asks us to look at the library of parent functions and identify the multiplicity of each zero in the identity, squaring, cubic, and quartic functions. So I have for us a picture of all 4 of them. I pulled these directly from the library of parent functions page, and I want to look a little more closely at the zeros that go with them. So let's look specifically at the identity function. So with the identity function, we are looking at the equation f of x equals x. And if I want to calculate the zeros for this, I would just say let f of x be equal to 0, in which case I would immediately get the answer x equals 0. And x equals 0 is going to have a multiplicity of just 1. So I'm saying times 1 for multiplicity of 1 there, just a little shorthand. So this is a perfect example for illustrating what multiplicity of 1 is supposed to look like. So look closely at the origin where your x-intercept is, and notice that you are just crossing through the x-axis, just a normal cross through. This is what a multiplicity of 1 is supposed to look like. Now let's look at the squaring function. With the squaring function, we have the equation f of x equals x squared. So again, if I wanted to calculate the zeros, I would have to say, let's let f of x be equal to 0, and then we would get the statement x is equal to 0 again. But keep in mind that the x here is being squared, which means that the 0 is actually here twice. So we would think of that as having a multiplicity of 2. So if I go to the x-axis at 0, which is where the x-intercept should be, so keep in mind that when I say x equals 0, that can also be translated into the ordered pair 0, 0. So we have the ordered pair 0, 0 as our x-intercept, and with the squaring function, we are not going to be crossing the x-axis. In fact, it says the graph will have a relative extrema at the 0. So when we talk about relative extremas, that means we're going to either have a relative maximum or we're going to have a relative minimum. So for the parent functions, these are going to be a very simplified version of what we could potentially get out of just a generic polynomial function. So here we just have a basic parabola, and you can see that we have a relative minimum located at the origin for that squaring function. Not crossing, but we are touching at that point, and we have a relative extrema. This is what a multiplicity of 2 is supposed to look like. Multiplicity of 3 is going to be coming from something like the cubic function, which is f of x equals x to the third. So if I have f of x equals x to the third, and I let f of x be equal to 0, then I would end up with, surprise, surprise, x equals 0, which can be interpreted as the ordered pair 0, 0, and we can all see that there is the origin marked on the graph. But the multiplicity of the origin, it's there 3 times. So what does the table say about the multiplicity for 3? It says that the graph flattens before crossing the x-axis. So this is very similar to a multiplicity of 1, except we have to have this little flattening effect. So you can see that the curve crosses at the origin, but it has this interesting little curvature to it there. So when I think about flattening, there's one of 2 ways that can happen with the multiplicity of 3. It can be like this, which is what the cubic parent function looks like, or it could potentially be in the other direction where it looks a little bit more like that. So those are the 2 options that we would have whenever we're trying to graph a multiplicity of 3 x-intercept. And then the last multiplicity that I want us to focus on is the multiplicity of 4. This is given by f of x is equal to x to the 4. This will be a real good example for us to see. This is the quartic function, and with the quartic function we are again going to get 0, 0 as the x-intercept. So I'm not going to show that step. You can see how that would come out. But the important thing for us to see is that we're going to end up with a multiplicity of 4. So with the multiplicity of 4, we are expected to have a flattening before becoming a relative extrema. So it looks very similar to multiplicity of 2, because we're not crossing the x-axis, but we're just touching the x-axis. But you can see that it's definitely flatter at the bottom than the parabola is. So this is why we typically call the quartic shape a U-shape, and then the quadratic or the squaring function is more of a parabola shape. That's because the quartic function has a higher multiplicity, and therefore it has to be flatter at the bottom. So this is the 4 multiplicities that you'll be responsible for when graphing a polynomial.